Today, we are talking about a discovery that completely flips the script on what we thought we knew about matter, right down to its most fundamental level. We're talking about the creation of stable, two-dimensional metals.
So what if you could make metal that was just one atom thick? I mean, really think about that for a second. A sheet of metal so impossibly thin, it's literally a single layer of atoms. What would that even do? For the longest time, this wasn't just a hard thing to make.
It was supposed to be straight up impossible, like breaking the rules of physics impossible. But, well, if you're about to see, someone just broke the rules.
Okay, so to really get why this is such a mind-blowing breakthrough, we got to start with the why not. Why did everyone think a single layer of metal would just fall apart? It all goes back to the very basics of what makes a metal, well, a metal.
All right, picture any chunk of metal you've ever seen. Inside, its atoms are all lined up in this perfect orderly grid, right? But the real magic is this sea of electrons that's just flowing freely all around and between those atoms. That sea is the glue. It's the metallic bond. It's the whole shebang. Now, in a regular 3D block of metal, that electron sea is totally surrounded. It's happy, it's stable, it's locked in place. But what happens if you shave it down to a single 2D sheet? Suddenly, that sea is exposed to the world. The atoms and electrons on the surface have nothing holding them in, and everything just goes haywire.
And I mean, it gets ugly fast. The atoms on the surface have way too much energy, so they immediately try to bunch together. That perfect atomic grid, it twists and buckles to try and save itself. And that all-important sea of electrons, it literally starts to leak out. So what do you get? Not a nice flat sheet, no way. You get a mess of tiny, separate little islands of metal. And for decades, that's where the science stopped. It just couldn't be done.
But then, a team came along with this brilliantly simple, almost counterintuitive idea. They realized the trick wasn't to fight against these chaotic forces, but to use a different force to trap them.
And let's be clear, this wasn't just a small step forward. This was, and I'm quoting the researchers here, a conceptual leap. It completely rewrote the rulebook on what's possible with matter. So you're probably asking, how on earth did they pull it off?
Okay, get this. They basically invented a molecular panini press. Seriously. They start with a tiny bit of metal powder on a perfectly flat surface, and they heat it up till it melts. Then, and here's the genius part, they slap another flat layer on top and just squeeze. As it cools down, that pressure forces the metal atoms into a perfect single atom thick sheet, all while being safely trapped, encapsulated by the layers above and below.
You have to understand, this new method just completely blows the old ones out of the water. All those other techniques, they can only ever make those useless, disconnected little islands we talked about. But this new squeezing trick, it creates big, stable, continuous sheets. And the best part? It's not a one-trick pony. It works for a whole bunch of different metals.
So, okay, they solved the impossible problem. Check. But what do they actually make? What are these new ultra-thin materials really like? Well, this is where the story gets even crazier.
Yeah, this wasn't just a fluke with one metal. They managed to create a whole new family of 2D materials. We're talking stuff you know, like tin and lead, but also some really interesting ones like bismuth and gallium.
Okay, now I'm going to throw a number at you, but stick with me. 9 million Siemens per meter. I know, that probably doesn't mean a whole lot by itself, but what it is just astounding.
That number, that's the conductivity of their 2D bismuth. And here's the kicker. It's over 10 times more conductive than regular, boring 3D bismuth. Think about that. They squished it down to practically nothing, and it became a better metal. A much better metal. Nobody, and I mean nobody, saw that coming. And the weirdness just kept coming. These things are super stable. They last for over a year as long as they stay in their little sandwich. And by forcing the electrons into that flat world, their quantum behaviors just go wild. They found something called a giant nonlinear Hall effect that was orders of magnitude bigger than anything seen before. Oh, and you can tweak their electronic properties with an electric field. You can literally dial their conductivity up and down. You just can't do that with a normal piece of metal.
All right, so this is the point where we shift gears. This stops being just a really cool physics experiment and starts becoming something that could actually change everything. Because what we're looking at here isn't just a new material. It's a brand new Lego block for building the future of technology.
And that's the real takeaway here. This isn't about making a slightly better wire. It's about having a whole new foundation, a new platform to build the next generation of computers, electronics, you name it.
So for nanoelectronics, the impact is like right now. Imagine the tiny wires inside your computer chip, the interconnects. Now imagine them being just atoms thick, but still outperforming copper. We're talking smaller, faster, and way more energy-efficient chips. Or how about flexible screens that are also transparent and conductive? The kind you could literally roll up and put in your pocket.
And for quantum computing, this is a potential game changer. One of the biggest hurdles is just building quantum bits, qubits, that don't fall apart. Well, it turns out these heavy 2D metals, like bismuth, are almost perfectly designed for controlling quantum information. They could even lead to qubits that are naturally more stable and error-resistant, which is huge.
But it doesn't stop there. This could even help with energy and climate. Because almost every single atom is on the surface, these sheets are amazing catalysts for chemical reactions. Think about turning harmful CO2 into useful fuel. And their knack for moving charge around super fast makes them a prime candidate for the next wave of batteries and energy storage.
So let's just recap. We went from physically impossible to a whole new technology platform in the span of just a few years. It just goes to show you that there are still these massive fundamental discoveries waiting for us at the tiniest scales imaginable. It opens up doors we're just now starting to peek through. The question isn't if we can build with atoms anymore. The real question is, now that we can, what are we going to build next?